Hi, my name is Boulem Hamouda. I'm with NEST, and I would like to talk to you about neutron applications in research. Uh, these include neutron activation analysis, radioisotopes applications, neutron radiography, neutron depth profiling, neutron processing. All of these 5 applications involve neutron absorption. And finally, neutron scattering, which doesn't involve neutron absorption but neutron scattering. These 5 applications are mostly inside the confinement building of our reactor, while neutron scattering is mostly in the guide hall. Let me show you schematics of the guide halls. At NIST we have an old guide hall and a new guide hall. Here we see the neutron source and a couple of 30-meter size instruments and so on and so forth. Go over some brief history of this field. 1942, the first controlled nuclear fission reaction, Fermi steam. Remember that neutrons were discovered in 1932, that was 10 years ago, 10 years before. Followed by a construction of many reactors. The first one, CP, they called Chicago Pile. Why? Because the first Fermi steam reactor, demonstration was in the University of Chicago Stadium. CP1, CP2, CP3. At NIST, that was CP5, 1966. In 1955, the first university-based nuclear reactor was built at Penn. In the 1960s, the first power-producing nuclear reactors were built. These were mostly pressurized water reactor, PWR. I'd like to mention that in 1979 there was a nuclear accident at 3 Mile Island. 1986, another accident in Chernobyl, and then just recently 2011, accident at Fukushima gave bad reputation to the field. Show you stable and unstable elements. This is the number of neutrons, number of protons in the nuclei, various elements. Stable ones are shown circle here, and the radioactive ones, the unstable ones, are shown below the curve. They are beta emitters, and above this curve, this variation, is positron emitters. One can see that all of the stable ones are to the right of this n equals z line, which means they have excess neutrons. We see alpha emitters are very heavy over here. The beta emitters are produced using nuclear reactors, while the positron emitters are produced using particle accelerators. Let me show you a couple decay schemes. Like, for example, the beta decay of gold-198 into mercury-198. Neutron gets absorbed in gold-197, gives gold-198, which decays by beta, in other words, emits an electron, and gives mercury and antineutrino. So this is the case of positron decay, carbon-11 to boron-11. And this is alpha decay. Notice across 3 squares. Again, pretty much the same figure, the same table, but in the form of tiles. Here we see hydrogen, deuterium, helium, and so on and so forth. It's almost like nuclear physics type of architecture. This is a wall at NIST, close to the radiation physics building. One nuclear reaction, nuclear fission. Neutrons are absorbed in a heavy fissile nucleus like uranium-235, plutonium-239, gives off two fission fragments and a couple of neutrons which get slowed down and used either to sustain the nuclear reaction or for neutron scattering. I'd like to mention that less than 1% of the neutrons are emitted from the decay of fission fragments. They're called delayed neutrons. Even though it's a small fraction, these delayed neutrons are essential for the safe operation of nuclear reactors. Nuclear fission, we see the belly of the beast here. In other words, the core of a nuclear reactor at the University of Missouri. The blue glow is due to what is called Cherenkov radiation. These are relativistic beta particles, electrons, that are emitted by fission fragments, and they emit this blue light while slowing down in water. Major facilities in the United States, major reactors, High-Ferrat Oak Ridge, and NEST. Let's get into neutron activation analysis and show you a spectrum right off. So in other words, samples are irradiated, they become radioactive, they emit gamma rays, and then we measure these gamma rays. We get all of these peaks, photo peaks. So the peak position characterizes which element is being detected, and this is a very sensitive technique. And the area underneath the peak determines the relative fraction of that element. Can measure down to ppm and even lower. We see cobalt, iron, and so on. Few applications: biomedical studies and environmental monitoring. Assessing calcium levels in the body allowed the study of disorders such as osteoporosis, for example. It was found that selenium deficiency has been observed in very old people and patients that received organ transplants. The presence of aluminum in the brain has been linked to Alzheimer's disease. Trace amounts of mercury have been detected in the hair of fishermen in Japan, 1970s. Abnormal levels of mercury in fish lead to kidney disorders and so on. There was a food poisoning crisis in Spain in the 1970s whereby 300 people died. Poisoning was traced to the presence of chlorine in consumed olive oil. Apparently large amounts of cheap and toxic seed oil was added in order to make profit. Trace amounts of palladium and platinum used in catalytic converters have been found in lung tissue of urban dwellers. Let's look at another application of neutron activation analysis: extension of dinosaurs. A thin layer of iridium was detected by NAA. It was detected about 256 meters down deep. Was deposited by the impact of a huge meteorite related to the extinction of the dinosaurs. The peak in iridium at 256 meters deep was correlated to a minimum in pollen-spore ratio. In other words, impact of the meteorite was followed by death of vegetation. This happened 256 meters down, in other words 65 million years ago. This is a contribution by Alvarez. Another application of NEA, volcanic eruption history from tree ring analysis. A 500-year-old tree was cut down, and then pieces of wood from each one of the rings, in other words, correspond to different years, were analyzed using NEA. Trace amounts of gold were detected in these tree rings related to documented volcanic eruptions over the past 500 years. This study was done at Penn State. Another application in archaeology. NEA was used to determine the provenance of art objects. In other words, where did they come from? A Greek vase shown here, and some statistical clusters. In other words, the relative amount of one element was correlated with relative amount of another element, like two metals contained in the vase, through neutron activation analysis, and then there were these statistical clusters were formed. If an art object belongs to one cluster, chances are it has the same origin as the other ones. Art history. Painting was activated, then X-ray film was put in contact with the painting after activation at various times. This is called the autoradiography. This is the painting of the Flemish painter Van Dyck, 1624, presenting Saint Rosalie interceding for the plague-stricken of Palermo. This auto painting, this autoradiography showed underneath the painting the self-portrait, the auto-portrait of the painter. This turned out to be the only known auto-portrait by this painter. Second topic, radioisotopes applications. First, natural radioisotopes. This shows a plate, ceramic plate, coated with a Fiesta red glaze, which contains uranium-238, natural radioactive element, which is radioactive. This technique of using uranium-238 and the red glaze was stopped in the 1970s, but one can still find such plates in second-hand stores and so on. Second example, I went to a food store where they have what is called salt, in other words sodium chloride, and no salt, it's potassium chloride. In potassium is 1%, which is potassium 40, which is radioactive. So this salt is slightly radioactive. These are minute levels. They're not dangerous at all. But still, interesting to see that Geiger counter picks up the radioactivity. Radio dating. There are a couple of applications. Carbon-12 is a stable element, while carbon-14 is radioactive. So, in other words, carbon-12 and carbon-14 get absorbed by living things. When something dies, carbon-12 level remains the same while carbon-14 starts decaying. Determining the ratio of carbon-12 to carbon-14 is used for radio dating, just like a time clock. Uranium-234 decays into thorium-230 by emitting an alpha particle. Both elements got trapped and during the formation of rocks and other geological formations, then over time uranium-234 decays out. So determining the ratio of U-234 to thorium-230 is a way of measuring the time clock rock formation over hundreds of thousands of years. Another method is the decay of rubidium-87 to strontium-87 is used to date igneous and metamorphic rocks over billions of years time scale. Remember that the age of the universe is around 14 billion years. Another application, medicine, radioisotope generator. Molybdenum, called Moly-99, decays into technetium-99 with a long half-life, 67 hours, which itself decays into technetium-99 with a short half-life, 6 hours. This one emits energetic gamma rays, while this one emits soft gamma rays, X-rays. So the second decay is appropriate for imaging, like for example imaging of the brain. So in other words, this is such a short half-life that technetium-99 cannot be produced at a reactor then taken to a hospital to do brain imaging. So what happens is this element is produced and then stored in what is called radioisotope generator and decays. Then just before injection to the patient, technetium-99 is flushed down into a vial, and there is 6 hours to image the brain and so on. These are referred to as cows that are milked on site, used for brain surgery, among others. Another medical application of gamma ray imaging is what is called the lexiscope imaging. It uses iodine-124, which when irradiating a reactor gives iodine-125, gives off soft gamma rays with a reasonable half-life. So in other words, when the patient cannot be taken to an X-ray facility, this is a handheld imaging device where one can take X-ray images. Let's say some other medical radioisotopes. Yttrium-90 glass microspheres are injected into the bloodstream to treat neoplasm. These are abnormal growth of tissue. These microspheres are some 30 micron in size. They get trapped in the liver, where they deliver their dose. This is for liver cancer therapy. Another application, palladium-103 seeds are implanted into the base of the prostate for radiation therapy of prostate cancer. Many of these seeds are implanted using long needles implanted into the prostate. Another application, rhenium-188 labeled monoclonal antibodies are used for the therapy of acute leukemia. They are cells, these monoclonal antibodies are cells that mimic white blood cells and end up concentrating in the bone marrow. Now some industrial applications of gamma ray imaging. There's the lexiscope again, but with iron 55, longer half-life. Also soft X-ray for imaging of metal parts, for example, to detect machine wear, locate cracks, leaks, examine welds, metals, and so on, like on a bridge or something that you cannot take to X-ray facility. Another application, like for example, nickel-63 emits charged particles which keep a constant current flow between electrodes. Smoke particles stop this constant flow and thereby detecting smoke. Nickel-63 is used in some smoke detectors because it has a very long half-life, about 100 years. There is no need changing batteries. Another application uses plutonium-238, which is radioactive, to produce very low intensity currents, just like batteries for heart pacemakers. Produces low current supply over a long time because the half-life plutonium is very long, so there is no need for additional surgeries to change the batteries on heart pacemakers. Another application is cobalt-60 irradiation. Food is irradiated to avoid spoilage and prolong shelf life. Many countries have approved food irradiation, like for example United States, the US FDA has approved irradiation of wheats and potatoes, spices and some fruits and vegetables, meat products and so on. Like for example, strawberries in Florida, pineapples from Hawaii are irradiated. There is a plant in Japan that irradiates some 40,000 tons per year of potatoes. International symbol for irradiation. I should mention that people have been reluctant to consume irradiated food, so it hasn't picked up that much. Next, let's look at cobalt-60 medical irradiation facility. This is for treatment of cancer. Cobalt-60 has a 5-year half-life, convenient for treatment of some forms of cancer like head, neck, spinal cord cancers and so on. The United States has some 12 cobalt-60 irradiation units per million people. Many countries have much lower numbers. Another application is the so-called gamma knife. It is used for localized radiation treatment of the brain. Treatment with surgery precision. Look at some other cobalt-60 applications. Sterilization of medical supplies. Treatment of domestic sewer, which after treatment becomes compost or fertilizer. There are sewage treatment plants in Boston and in Munich. Wood and raw wool products are irradiated before leaving Australia. Cobalt-60 irradiation is used to enhance reaction yields, like for example Dow Chemicals has an ethyl bromide production plant in Michigan. Next, let's look at neutron radiography, or so-called neutron imaging. Let's look at the radiograph of a camera. This is X-ray radiograph, and this is a neutron radiograph. Remember that X-rays and neutrons are sensitive differently to different elements. Like for example, light Z elements like plastics are completely transparent to X-rays but opaque to neutrons, while metals are completely opaque to X-rays while transparent to neutrons. Here we're looking at neutron imaging scintillator. It's also called converter plate. In other words, neutrons get absorbed in lithium-6 and give off 2 charged particles which are attracted by electrodes and trigger a detection event. CCD camera with a high spatial resolution gives a digital image. Let's look at the neutron radiography of a fuel cell. Hydrogen fuel cell uses hydrogen on one side which gets ionized and crossing a catalyst, so that the proton make it through a membrane, while electrons flow outside to give an electric current. Then these protons recombine with oxygen from air to give off water. So in other words, hydrogen fuel cells use hydrogen to produce electricity. In other words, hydrogen is an alternative fuel to petroleum. Let's look at the neutron radiography of the fuel cell. One can do real-time imaging of water flow inside the fuel cell. Like in this case, we can see that water accumulates close to the anode, likely due to heating. This is a project in collaboration with GM, who has a great deal of interest in hydrogen fuel cells for their cars. Other applications of neutron radiography, like visualize cracks inside metal structures and so on. Car engines, hydraulic systems. One can see the flow of oil, for example, in a car engine or hydraulic system, or so on and so forth. Visualize water intake and vegetation, germination of plants and so on. Visualize the inner contents of bronzes, like in one instance, Egyptian pharaonic bronze. Remember that bronze is opaque to X-rays, so neutron radiography is the only way. Turned out it had a bird. It was in the form of a bird, but it had bird skeleton inside. Let's move on to the next application, which is neutron gauging. Consists in lowering a small neutron source into a drilled hole. Remember, neutrons can see hydrogen very well, in other words, water or gas or oil, petroleum. So a neutron source is lowered into a hole, a well-drilled hole, and a neutron detector looks at reflected neutrons, reflected back, scattered, detected. This tells us whether there is water, natural gas, or oil, or something else. This is a wear survey, rock and mud content, a spike in hydrogen content, sign of oil, water, or natural gas bearing. A few other applications of neutron gauging, like determine moisture content in concrete. Determine the carbon to hydrogen ratio in hydrocarbons, so-called cracking ratio. Determine the hydrogen to nitrogen ratio in the various foodstuffs. The Mars rover mission planned on sending what is called the dynamic albedo of neutrons, a little device with a neutron source and a neutron detector, to be able to detect water near the Mars surface. As it turned out, this method was not necessary to find water on Mars surface. A much simpler method was used. The first rover used shovel at the end of telescopic arm to dig slightly. Then white stuff was observed. It was either salt or ice. After a while, it melted away under the sun. So in other words, it was ice that melted into water. Neutron depth profiling. The facility itself is a neutron beam that gets absorbed in a sample, skin deep. Then there's emission of two charged particles, which get out of the sample very near the surface, and then sitting outside, measuring the kinetic energies and the angle determines the depth of the nuclear reaction. This is a neutron depth profiling. Let's look at neutron depth profiling from boron, which absorbs neutrons, gives out two charged particles. Here we see two samples, one a thick boron layer, another one a thin boron layer. Boron is used uh, uh, boron dopant distribution silicon semiconductors. Boron is used as dopant in semiconductors. In other words, silicon that contain boron is a semiconductor. Silicon semiconductors are used in many applications. Another application neutron depth profiling from lithium, which also gives out two charged particles. And in this case, looking at distribution of lithium in an electrochrome material. This is material that changes color when we change the voltage applied. Case applications in color changing windows, and optical filters, and so on and so forth. One can determine the distribution of lithium close to the surface and find out why is the color changing, because the distribution of lithium is changing inside the sample. Other applications, neutron depth profiling. Boron is added to dielectric phosphosilicate to increase its melting point. Lithium is sometimes added to niobium to make optical waveguides. Lithium distribution was determined in lithium batteries. Concentration, sensitivity down to parts per million. Neutron processing, track etching, fission fragments. Tracks are used to date rocks. In other words, uranium-238 fissions, decays, long half-life, leaves a number of tracks. Counting the number of tracks tells us how old this rock formed. This method was used to date the eruption of a supervolcano some 75,000 years ago. This event was correlated with a spike in sulfur levels observed in ice core data in North Pole. The supervolcano 75,000 years ago was traced back to Lake Toba in Indonesia. There was another supervolcano some 2.1 million years ago in Yellowstone in the United States. Chromatography. Chromatography columns use microporous material, which is produced by fission tracks, uranium-doped glass. Chromatography is used for fractionation and so on and so forth. Like, for example, long molecular weight polymers diffuse down the column very fast, while short ones takes a longer time. So a method of fractionation allows us to determine the molecular weight distribution of these polymers. Another application, production of nucleopore filter. A polycarbonate film is made to pass next to a fission plate. The process of fission fragments create uniform pores in the film, changing the nucleopore filter material. In other words, they create holes. These are pores. Irradiation time gives us the density of these pores, and subsequent chemical etch gives us fixes the size of these pores. This is a industrial application. These types of filters are used in chemistry as well as molecular biology. Another application is transmutation doping of silicon semiconductors. Well, when under neutron irradiation, silicon changes into phosphorus 31, which is a dopant in semiconductors. Remember, we had said that boron is an N-type dopant in silicon semiconductor. Well, phosphorus is called P-type dopant in silicon to form semiconductors. N-type and P-type doped semiconductors are essential for making electronic devices and so on, like transistors and so on. phosphorus 31 acts as an electron donor. Transistor, IR detectors, energy production and storage, and so on and so forth. Then another application, neutron irradiation creates color centers and gemstones, like for example topaz goes from a transparent color to a nice light blue, which enhances its value. Topaz is mined in many countries. Some 13,000 pounds of topaz are irradiated every year worldwide, 40% of which is irradiated in the United States. Neutron capture therapy. Boron-10 tagged chemical agents are injected in patients, preferentially concentrate in the tumor. Remember that boron-10, when it absorbs a neutron, gives off two charged particles, creates damage in the tumor, cancer tumor. In other words, after injection, the patient is treated using thermal neutrons, which destroys cancer cells. But this technique of neutron cancer therapy has been used in Japan, in the US, and in Finland. Other useful applications of radiation damage, like radiating diodes, increase their electrical resistance. Radiation of memory chips helps reduce soft computer failures. Irradiation improves the hardness of drill bits. Let's pause for a moment and look into the perspective of all of this. Nuclear applications contain three main areas. Weapons. Weapons race ended with the Cold War. Some former Soviet republics gave up their stockpile to the United Nations, which is using it as fuel in nuclear reactors. This is as far as weapons production. And then power production. The oil crisis of the 1970s pushed reactor power to be increased to 1,000 megawatt electric, which prompted a series of accidents, 3 Mile Island, Chernobyl, and Fukushima recently, caused overruns of nuclear facilities, so that no new license in the US for the past 30 years. Nuclear waste has not been resolved. It's being stored, like Yucca Mountain, United States, and so on. I'd like to say that research reactors have reached saturation of technology. They have reached the maximum cooling capacity, something like 6,000 gallons per minute, something like this. The issue of fuel enrichment. All nuclear reactors were mandated to go down to medium or low fuel enrichment in 1979. However, this law has never been implemented or enforced because such fuels had not been developed, but now they have been after a long while, and all research facilities will have to go down to medium enrichment over the next 5 to 10 years. University reactors are a dying breed. In the US, there were some 50 to 60 built. There are 23 of them left. All of the others shut down. Of the 23, there are 12 that are under 1 megawatt, so only a few research reactors are left in the United States. And only 1 or 2 have been built over the past 20, 30 years. They're really a dying breed, but some research upgrades bring renewed hope. Next and last topic, neutron scattering. Let me show you a picture of the NIST old guide hall, a very busy place. See the 230-meter science instruments. It took us about 10 years to finish the construction of all of these instruments, from 1990 to 2000, something like that. The science instrument This was the first instrument, 1991, 1992, and so on and so forth. Then we started the user program, very busy place, exciting science coming through. And then around 2010, got funding for the new guide hall. Now it's built, and we're building instruments. Like this is a 10-meter size, and so on and so forth. This is going to give us another 10 to 20 years of excitement at NIST. Let's look at neutron scattering. This is the length scale inside the sample and the time scale of the dynamics within the sample. We say this is 10 angstroms, so this is now 1 nanometer, this is 10 to the minus 9 seconds. Remember that scattering methods are in Fourier space. There is a Fourier transform space, which is called the scattering variable. Fourier transform of time, which is the energy transfer during scattering. All of these are quasi-elastic, inelastic techniques, instruments like triple axis, time of flight, backscattering, spin echo, and so on. And all of these are called elastic scattering techniques, like small angle neutron scattering, reflectometry, diffraction, and so on. Let's look at a few applications in small angle neutron scattering, like wax buildup in diesel engines. Diesel engines do not run well in cold climates. Filters clog up due to wax crystal buildup. This is a collaboration with ExxonMobil. Adding polyolefin copolymer reduced the wax buildup, like we see here, micrograph of before and after adding the copolymer. We see that there is no more wax. SANS was essential in determining the structure before and after adding the copolymer. Microstructural changes in reactor vessels. Pressure vessel steels are irradiated to study the effect of long-term radiation exposure on embrittlement. In other words, steels become brittle when they get exposed to radiation for a long time. Alloy nanostructures were correlated to radiation hardening conditions. Hydrogen fuel cell again, with small angle neutron scattering, determined the structure of polymer membrane. Polymer membranes let only the protons pass through, and it was found that the performance of the polymer membrane is enhanced when pore size is smaller than 5 nanometer. Well, one can control these pore sizes, and therefore enhance the performance of fuel cells. Characterization of various marbles. Italian white marble morphology were characterized by small angle neutron scattering. Determined what is called the grain radius in the marble, and then the fractal dimension here, and then plotted many samples, many various types of marbles. So here also forming clusters, correlation clusters, like to identify the source provenance and authentication. If two marbles are in the same cluster, chances are they came from the same quarry. Other applications in conservation science. Some nanosponges were made to clean up paintings. Like we see here, after cleanup and before cleanup. The structure of these nanosponges were determined using SANS. These nanosponges are formed of various gels that contain surfactants. Were also used to clean up some Mayan wall paintings in Mexico. Final words. At NIST, Center for Neutron Research, we're having lots of fun. Not only our research effort, which produces some small angle neutron scattering, some 80 papers per year, about 200 experiments per year, We also have an effort of education outreach whereby every year we have 1 week long summer school, and we developed a distance learning course, 3 credit. Last time it was taught, had some 50 graduate students from all over the United States taking this course for credit, where they would get course material on a weekly basis, as well as homework that gets corrected, and live discussion sessions. Check it out. This is the website. This is my email address, and this talk has been recorded and available over here. Thank you very much.